Actually, these trig functions you're going to have to review. Like, go to the textbook. I'm sure there's a table in there somewhere. You need a note card for calculation. You really do. You need a note card of the derivatives of all of the trig functions, and you're probably going to need a note card for the integrals of all those things as well.
Yeah, just letting everybody know, in the front of the book, it has like basic differentiation rules and also basic integration formulas, in case you wanted to know that.
Yeah, pretty much that's it. Like that thing at the front of the book, it's a table. I would keep that table next to you or something equivalent. Like, so for example, if you don't know it, you should have it really like, close to you that secant squared is the derivative of tangent. Okay. So the solution to this would be very straightforward if you knew that. But if you saw immediately that that was the derivative of that, you're done. Right? Because if u is equal to tangent x, then du is equal to secant squared x dx. So you have du over u, and you're done. It's just the natural log of u at that point. So then if I had more room, I'd write it down there. But and what was u is tangent x. Okay. So everyone knows the derivative of at least sine, right? What's the derivative of sine?
Cosine x.
What's the derivative of cosine x?
Negative sine x.
Okay. So if you know that, we should be able to find this integral. Okay. So what do you think you should let u be in this case?
Technically, you can rewrite tangent as sine of x over cosine of x, so u would be cosine x.
Good idea. So this integral you can rewrite as this integral. Perfect. And so then you said let u be cosine x. So if u was cosine x, then du is negative sine x dx. So it's almost there, right? The negative is the only thing that's different, but you can fix that by just multiplying both sides by -1 here, and you get the negative du is equal to sine x dx. Sine x dx over cosine x, we can replace everything and write it in terms of u. So this is negative 1 over u du. So now that we've done this a few times, I'm taking out those constants immediately and writing them in front of the integrand. Okay. So then once we have it in that form, we apply the stem and we're pretty much done. So be negative natural log absolute value of u, but u is really that. Okay. Any questions on that? And again, like, you're probably going to forget this integral, but you need to have it on a table somewhere near you because it's going to pop up a bunch of times in the future. Okay. All right, and this next one is a little bit more involved, so I'm going to work out the whole thing for you. But I think that this example kind of illustrates the typical types of problems that you will encounter in calculus 2. Basically, nasty integration problems. So, find the indefinite integral for secant x dx. All right. So this one is annoying because of this following trick. So basically, the idea is that I don't know of anything whose derivative is secant, but I do know that secant squared is the derivative of tangent, right? And I do know that if I can get du over u, I can integrate this thing. So what I'm going to do is I'm going to multiply secant x by a fancy form of 1. I'm going to multiply it by secant x plus tangent x over secant x plus tangent x. Right? It has to, you only multiply by 1, so you see if I multiply by that on the top, I get to do it on the bottom. So why would this be useful? Well, this now becomes secant squared x plus secant x tangent x all over secant x tangent x. Dx. So now I'm almost there because what's the derivative of this guy here? Secant x. What's the derivative of secant x? It's something I'm sure all of you forgot from Cal 1.
You said the derivative of secant x?
Yeah.
The derivative of that, I think, is secant x times tangent x times 1?
Secant x times tangent x, basically. If you didn't know, how would you figure it out? So if you didn't know the derivative of secant x, how would you figure that out? You just use the definition, right? So this is kind of aside from this problem. Well, we do need to know the derivative of this, because if it's equal to that, then we're good. So it's not too much of a tangent to ask, how do we find out the derivative of secant x? Well, this is the same thing as looking at the derivative of what? What is secant x equal to in terms of cosine or sine?
1 over cosine.
Right. In other words, cosine x to the power of -1. Okay. So then now you just use the chain rule. So derivative of the outside -1 times the inside, right? cosine x. And that's all now to the power of -2 times the derivative of the inside, which is negative sine, right? So negative times a negative, it becomes positive, and we end up with sine x over cosine x squared, right? Or in other words, 1 over cosine x times sine x over cosine x. Or in other words, secant x times tangent x. So the derivative of that is that, and the derivative of that is that. Oh, it looks like we can do our u substitution and use that natural logarithm rule. So I guess I'll write it over here. What was it? That was the integral of tangent, right? I have a feeling we're going to need that at some point, so I'm going to save it over here. So now I'm going to write it. Okay, so still in this problem here, so if u is equal to the denominator, secant x plus tangent x, then du is equal to, so derivative of that we found out was secant x tangent x. And the derivative of that is secant squared x. And this is all yes. So du is equal to that. So if we look back over here, we get, oh, that's this there times dx, that's du, all over u. So this is just 1 over u du. So now this is equal to the natural log absolute value of u, which is this thing. And don't forget your constant integration. Okay. Okay. Let's look at one more example. Actually, 2 more examples. So this one says evaluate the definite integral 0 pi over 4 square root of 1 plus tangent squared x dx. All right, so again, these trig functions are going to throw you off at first, but you'll get used to them just because you'll end up seeing them so often. What's so nice about 1 plus tangent squared x?
It's equivalent to secant squared x.
It is. Does anyone know why it's equivalent? It's a consequence of, we know that sine squared x plus cosine squared x is equal to 1. That's like the most basic identity relating those 2 things, right? So sine squared plus cosine squared is equal to 1. So if I wanted to figure out what tan squared is related to, I could divide this entire equation by cosine, squared x, which would mean that sine squared x over cosine squared x. Cosine squared divided by cosine squared is just 1. And then we have 1 over cosine squared x. But this is just tangent squared, right? And then this is secant squared. So this identity here, we can throw in there, right? So then this becomes like that. Square root of a square, this goes away. Oh, and we just did that one here. So this is a rather long thing. This is natural log absolute value secant x plus tan x. And this is evaluated from 0 pi over 4. Whatever that becomes. Yeah, it evaluates as something. I'm not going to think too hard about it. Okay. One more. All right, so this says solve the differential equation dy dx equals to 1 over x natural log of x. So a differential equation is just, we just want to find the antiderivative. We need to know what y gives you that, right? That's all it is. So if the derivative of y is that, then the integral, the indefinite integral, is the original function. And that's what solving a differential equation is. You have an equation in terms of derivatives and you want the original function. So in order to do this, I can just note that that y is going to be equal to the antiderivative of this statement, of this equation. And now here, I don't see u prime over u anywhere in there. So it's not clear how I can do that. But I can do one thing. I know the derivative of natural log x is 1 over x for x positive. Okay? And x will be positive because natural log of x has to be positive. So I can do this. I can multiply the argument here by 1 over x divided by 1 over x. That doesn't change anything, right? Because it's just a fancy form of 1. And what this integral becomes then is 1 over x all over natural log of x dx. When I do that, right? X times 1 over x is just 1. So that those x's go away. And we have 1 over x in the numerator, natural log x in the denominator. And now I see it. This is u prime and that's u, right? You let u be this guy right here. So then if I let u equal to natural log of x, then du is equal to 1 over x dx. Right? And x is positive. This guarantees that. So I don't need the absolute values or anything for this one. So altogether, this is going to be natural log absolute value of u, which is ln x. And your constant of integration would yield a solution to the differential equation. If you have like an initial condition, you could solve for that. But that's the general solution to that differential equation. Okay. So from this section, section 5.2, yeah. Yeah, I'm gonna have to suggest a lot of problems. Basically, 1 through 57. Okay, so those are suggested homework problems. I'm gonna pause or stop the recording here.